Next, we have a list of set identities. These set identities are the same as comes out of the book. You've got a variety of identities, all listed as different laws. The big thing with these identities, there are two different ways to go about grasping these. One, you could go about a formal proof, where you go back to the definitions and you prove which elements are in which set, and you can go through a complete actual formal proof. And the other way is to just get an idea of what's going on, and you can do that through the use of Venn diagrams. So I'll just kind of scroll through these for a second, and then go to a new page, and we'll take a look at Venn diagrams for a couple of these, just to show you how you would use a Venn diagram to quickly and easily prove to yourself what's going on in an identity. So let's go first with A intersect the universal set is equal to A. And this is one of your identity laws. Draw your Venn diagram for this. Got the universal set labeled there. Got this circle for set A. And again, we'll go to red for our shading color. So if you've got A here, we'll shade the circle A. And then we say we're going to intersect that. Those are all the pieces that, all the elements that are in A and in the universal set. It leaves you with the exact same thing. Easy to see in a Venn diagram. So that one, although not a formal proof, is a nice informal way to show yourself exactly what's going on here. Similarly, we could do a, oops, go back to blue. We could do a union, the empty set is equal to A, and maybe change this color to green, and I'll shade A in green. And if I union that with the empty set, well, the empty set has no elements, so just what's already shaded would be what's shaded. So it's nice and easy to use a Venn diagram to identify what's going on in some of these. Next, let's take a look at DeMorgan's laws. And we've set up two Venn diagrams here. And on the one over on the left, I'll do A intersect B. And then take the complement of that and show that that is equal to the one on the right, which is the complement of A, union the complement of B. So to start off with, we're going to need a couple of different colors here. So let's start with the color red. And over on the one on the left, we'll do first the intersection of A and B. And that would be all the elements that are in both A and B. Then to take the complement of that, we'll switch colors over here, and we'll do yellow. So this is everything that is not the shaded red that's in A and B. So that is all of the stuff that's in A, but not in B, and all the stuff that's in B, but not in A. All right. So then over on the one on the right, let's take a look at the complement of A. Okay, so if I go with the complement of A, that's everything that's not in A. So that's all the stuff that is in B but is not in A. All right, then let's go and use green. The complement of B, that's everything that is in A but not in B. So we see what we have left over here is that the chart on the left is the same as the chart on the right. If I put my legend out here, I'll put yellow shading is A intersect B's complement. And then over on the one on the right, the yellow shading is the A complement, and green shade is the B complement. So together, they are complement of A union the complement of B. And therefore, the Venn diagram on the left matches the Venn diagram on the right, and we've done an informal proof showing that these two are the same. Of course, that's not good enough to do for a formal proof, but it is very good to easily and quickly give yourself an idea of what's going on. Next, we'll take a look at doing this through a formal proof. So now we'll prove that A intersect B's complement is equal to the complement of A union the complement of B. And this is one of the DeMorgan's laws. And in order to show that two sets are equal, remember that we must show that each is a subset of the other. So we'll need to do two parts to this proof. So for part number one, we'll show that the A intersect B complement is a subset of the complement of A union the complement of B. That'll be first. So to start this out, we'll go let X be in the A intersect B complement. And that means, by the definition, that X is not in the intersection of A and B. By definition. Notice, like always in proofs, we come back to definitions to start things off. And then we'll take that definition and we'll expand it, and we'll say this means that, and maybe I won't use the bar over the top for negation here, since that's what we're using for intersection. We use that symbol instead. So we'll say the negation of X is in A, or negation of X is in B. And this is DeMorgan's laws for propositions. Okay. So what does that mean when we look at this? Well, that means that X is not in A, or X is not in B. Definition of negation. And therefore, we have X is in the complement of A, or X is in the complement of B. This is the definition of complement. Okay, so now we've proven the first part of this. We'll scroll down a little bit, and we'll attempt to prove the second part of this, which is the complement of A union the complement of B is a subset of A intersect B complement. So we'll let X be in complement of A union the complement of B. And we'll expand this out. That means that we've got X is in the complement of A, or X is in the complement of B. And let's see, say that was definition of union. That allows us to go there. Then we'll say, all right, X is in, X is not in A, or X is not in B. And this is definition of complement. And we'll go on to the next step. We'll say, okay, then we have the negation of X is in A, and the negation of X is in B. And then if we're going to pull that negation out using DeMorgan's laws, we can do that. And when we do that, we'll end up with X is in A, and our sign flips. So instead of or, we'll have and. X is in B. This is by DeMorgan's laws. For propositions. And then now we have this, we can say, okay, that means that X is in A intersect B. How can we say that? Well, that is the definition of intersection. If X is in A and X is in B, then X is in the intersection. Okay? now using the definition of complement, we can say, okay, then that means X is in A intersect B's complement. And this is using definition of complement. So now, we said, since shown part 1 and part 2, that is, one was a subset of the other, and then the other was a subset of the one, the sets are equal. And then we're done.